Another rule that you're going to need to use to solve counting problems is the divide rule. Now, the divide rule is most commonly thought of in relation to dividing out duplicates in a combinations or permutations problem. However, in general, the divide rule can be used in any circumstance. So in this video, I want to make sure you understand in general what the divide rule means and how you can apply it in general. And so all you're doing with the divide rule is you determined a count of some event or some system, and you want to divide out a portion of that count that you don't need. That's the divide rule. Again, you have a count that you've determined from some system or some event. So you have a count, but you want to divide out a portion of that count that you don't need. That's the divide rule. Okay, and what you can think about is in developing the basic permutations formula and combinations formula, we used the divide rule. Now, I just want to note, though, that it's not like if you're trying to solve some permutations or combinations problem that you don't have to use the divide rule anymore because it was already used to derive these formulas. No, that's not how it works. It depends on the specifics of the problem. You can use the divide rule in all kinds of circumstances. Again, it's just whenever you want to divide out a portion of a count that you don't want. So maybe you applied the NPR formula and you got some count, but then you look at the count and say, okay, but I need to divide out some stuff here. Okay, but regardless of how you use the divide rule, what you're fundamentally doing in all circumstances is the same idea, just dividing out the portion of a count you don't want. So let's go back to how we used the divide rule for these basic permutations and combinations formulas, just to get a feel for exactly how this rule was applied in these circumstances. And then we can branch out to some more general applications. Okay, so with NPR, we had a group of objects or elements or people, a group of N objects, and we were selecting from that group R objects. Say in this case, R would be equal to 4. So, okay, we could say N is equal to 50 and R is equal to 4. And the goal was to count the number of different arrangements of these 4 objects that were selected from this group of 50. Okay, the answer to this question was, so you have 50 times 49 times 48 times 47, and that's it. That's the answer. But where this answer came from was that we thought about how you start by taking 50 factorial, N factorial. That's the number of different ways you can arrange 50 items in a line. So you have a group of 50 items, and then so from there you have these 50 slots, and you're just picking from that group of 50 and putting different people into those slots, different objects into those slots. Okay, but since we're only picking 4 in this case, then what we want to do is, so 50 factorial we would continue the slots until we got 50 slots. Right? Well, we aren't using these last 46 slots. Yes, we're still picking from this group of 50 for the first 4 slots. So we need 50 times 49 times 48 times 47 times 46. But we don't need to continue the full 50 factorial, or no, it went down to, it was just 4 slots. So we don't need to continue with the remaining 46 slots. So what we're wanting to do is divide out that 46 factorial, that full count of the different ways to arrange 46 items in a line. And then we get exactly what we want. The number of ways you can arrange 4 items in a line if you're picking those 4 items from a group of 50 items. And that's the formula for NPR. And if we look at these 4 terms here, this makes sense. because the first slot, there's 50 items, but there's 50 potential outcomes. The second slot, there's 49 potential outcomes. Third, 48. Fourth, 47. Well, okay, this slot could have been any one of the 50 items. Any one of them. This second slot could have been any of the remaining 49. But if we chose, like Jack first, then Sam second, well, we could have chosen Sam first, then Jack second. That's included here. This is any of the 50 items. But we're only arranging 4. We have 4 slots where we're counting the arrangements of 4. So we stop at 47. But because this is 50, 49, 48, 47, we're accounting for all of the different possible 50 selections that we could have put into this group of 4. Okay, so that's how the divide rule was used to derive the fundamental permutations formula. Okay, what about the combinations formula in CR? In choose R. Okay, well, it was the same idea. You had this group of N objects, let's say 50 objects again, and you're picking R objects to arrange. Let's say R is 4, and you're wanting to count the number of arrangements of R items that you picked from a group of 50, 4 items that you picked from a group of 50, but you don't care about order. You don't want to count different rearrangements of the same group of objects. Okay, and so to come up with this in choose R formula, the whole idea is we want to calculate the number of permutations for selecting R items from a group of 50, the number of different arrangements. So in PR, but then from that, we want to divide out what we don't, the count we don't need, which in this case is going to be the number of ways you can arrange 4 items in a line. So the result here would be you do 50 factorial divided by 46 factorial, and now you have the number of permutations, but then you divide out 4 factorial. And now you have the number of combinations. That's what you're looking for. So this formula then is n factorial over n minus r factorial times r factorial. Okay, but how does this work, though? Why does dividing by 4 factorial work? Well, okay, we can think about this, and this is actually going to be a little more intuitive for understanding the divide rule than the permutations case. So if we start with NPR, so if we started with, let's say this count here was 50. Okay, so that's 50P4. The number of ways you can arrange, picking 4 items from a group of 50, the number of ways you can arrange those items in a line, where the order matters. Okay, well, we can break this down, this 50P4 down. We could make an event diagram here. So here's the system. Here's event 1. Here's event 2. Okay, we can break this down as, let's say that event 1 is exactly what we're looking for as far as combinations. So it's the number of ways you can arrange. You can choose 4 items from a group of 50, the number of ways you can arrange those 4 items in a line, but order doesn't matter. You don't want to count rearrangements of the same group of items. Let's say it's exactly what event 1 is. That's exactly the count that we're looking for, and let's say that's M. We don't know what this is, but we can hypothetically say that's exactly what this is. Okay, now let's say that event 2 is the number of ways you can arrange 4 items in a line. So that's just 4 factorial. That's like 4P4. Okay, if we applied the product rule between these 2 events, so if these 2 events were connected, so let's say this is N outcomes, what would that mean here? Well, okay, we can intuitively think about the product rule from the perspective of, so you're taking each one of these M outcomes. Let's say there's 50 outcomes here. You're going one by one through each of these outcomes, pausing it on an outcome and then cycling through all of these, 4 factorial. Then you're going to another outcome, cycling through 4 factorial again. Going through another outcome, cycling through 4 factorial again, right? So now, but what is this though? What is M? Well, M is, it's what we're looking for in terms of these combinations, and we can think about it as, you could take a picture of each of these M's. You could take a snapshot. Well, if you compared all of those snapshots, you would never see the exact same group of 4 items. You would see the same item in multiple pictures, but you would never see the same 4 groups of items in the same picture, ever. Okay, so with that then, what is M times N? What does that represent? Well, what you're doing is you're stopping at each picture of M, which is this unique group of 4 items together, that the only one time those 4 items are together in a picture, you're pausing on that picture and you're cycling through 4 factorial. And so you can think about that 4 factorial represents the number of ways you could arrange the 4 items in a line in that picture. Okay, but then you go to the next picture with 4 other distinct items, and you cycle through that 4 factorial times. Then you go to the next picture, cycle through that 4 factorial times. Okay, and so with that then, what you can see is M times N is 50p4. That's exactly what M times N is. It's the number of ways you can arrange 4 items if you're choosing from a group of 50 and you care about the order. Even if you have the same group of items, you still want to count different rearrangements. That's exactly what this multiplying these 2 events is. This is equal to M times 4 factorial. Okay, well, but what are we looking for? What are we trying to solve for? We're trying to solve for M here. That's what we're looking for. So there's your explanation that to solve for M, you just take the number of permutations, this 50 times 49, 48 times 47, 50p4, and divide it by 4 factorial. So you see, we divided out the duplicates. And that's why the general combinations formula in CR, in choose R, you start by writing out in PR. So in PR is, there's in PR, but then you add in the denominator the number of slots factorial. And there's the divide rule right there. Okay, now that we have a better sense for what the divide rule is and how it's applied, let's look at an example application that's a little bit different than how we just saw it applied for the combinations formula. Okay, so let's say we have the word Atlanta. Okay, the question is, how many different ways can we arrange the letters of the word Atlanta in a line? So here's one, right? But another would be, right? There's another. So what's the total number of ways you can arrange the letters of the word Atlanta? Okay, well, we would start with just thinking about a basic permutation problem here, right? The number of ways you can arrange 1, 2, 3, 4, 5, 6, 7 items in a line. There's 7 items here. Okay, what's the number of ways you can arrange these items in a line? So 7 factorial, right? You've got 7 slots. So there's 7 possibilities for the first slot, 6 for the second. Right? However, there's an issue here. If all of these letters were different, then that would be the correct answer, just 7 factorial. However, if we just say 7 factorial, then we're counting the idea of if this letter and this letter switch spots, or this letter and this letter switch spots. Well, that's the same arrangement. Okay, so what we need to do is we need to divide out these duplicate cases. So how do we do this? Well, the answer is, what we're going to do is we're going to say, so we've got 7 factorial. That's the number of different arrangements if these were all different letters. But we're going to divide out, so we've got 3 A's. So we're going to divide by 3 factorial. And we've got 2 T's. So we're also going to divide by 2 factorial. And this would give us the answer we're looking for. All right, but why does this work? How exactly does this work? Well, okay. If we think about 7 factorial, in the case where all of these letters were different, well, mixed in here are all of the different ways you can arrange the 3 letter A's and the 2 letter T's. This could have been the second letter A. Then this could have been the first letter A. This could have been the third letter A. Or this could have been the third letter A. This the second, this the first. Or this could have been the first letter T, this the second letter T, or this the second letter T, this the first letter T. For any given arrangement, you're pausing and cycling through all of the ways you could switch the 2 T's, which would just be 2 ways, right? For any given arrangement, you're saying, okay, we want to pause and count. Well, we could have switched the 2 T's, and then that's it for the T's. But also, you're staying paused, and you're cycling through, okay, I could have switched the first 2 A's. I could have switched the first and the third A. I could have switched the second and the third A. That's 6 different arrangements, right? So for this arrangement here, Atlanta, for this count here, we would pause and say, okay, we're paused here. Now, one of the things we're doing is we're thinking about, okay, we could have swapped. We want to count an arrangement where we swap the 2 T's. Then we want to count the 6 different ways we could rearrange the 3 A's. Then we're going to another arrangement. Okay, pausing, saying, okay, we want to count. Well, one of the things we're counting, we're pausing here, and one of the things we're counting is we could switch the 2 T's. So we want to add a count. All right, now we could rearrange, there's 6 ways we could rearrange the A's. We want to count all of that. But then it's also paused and counting. Well, we could switch the L and the A, switch the A and the N. And we actually do want to count those counts. Those are fine. Those are legitimate. So what we're wanting to do is we're trying to tell the algorithm, look, every time you pause on an arrangement and start counting the different configurations. So when I say pause on an arrangement, you could think about this from any perspective you want. You could, all right, what if the T was first? All right, cycle through all of the different arrangements, right? It's just the way you look at this multiplication process. But we're trying to tell the algorithm, when you're kind of paused on an arrangement and you're cycling through the different potential rearrangements, don't count the different ways you could rearrange the 3 A's, as well as don't count the different ways you could rearrange the 2 T's. And all that is for the A's, that's 3 factorial, and for the T's, that's 2 factorial. Okay, and so that's the fundamentals of the divide rule. Now, you might be asking yourself, well, what about for something like, okay, let's say we had the word Atlanta. All right, but instead of counting the ways we can arrange all of these letters, what if it was something like we're picking 3 of these letters from this group, and now we want to count the total number of ways we can arrange the different 3-letter groups. So, L, N, T, that would be one arrangement, but then we could arrange these 3 factorial different ways. So this would be like 6 arrangements, but then you could bring in an A instead of the N. This would be 6 more different arrangements, but you could bring in another A here. All right, but now we don't want to count, rearranging the A's. So how would you apply the divide rule here? Well, this is a little more complicated of an example where, for examples like this, these more complicated examples, we're going to be needing to apply multiple rules at once, multiple rules or multiple types of counting problems, so like permutations, combinations mixed in with the sum rule, etc., which is how general counting problems are going to work. And so what we're really trying to do in all of these different lecture videos on counting, so the lectures about what a permutation is, what a combination is, what the divide rule is, what the sum rule is, etc. We're just trying to get the basic concept down of what these rules and formulas are and look at some basic example problems on how to use them. And then later, a few videos from now, we'll start getting into some more realistic example problems that require us to use multiple different rules and formulas within the same problem, which would be the case here. So at the moment, don't worry about a problem like this. For this video, just try and understand the fundamental concept of what we're doing with the divide rule. How we're obtaining a count and then dividing out outcomes from that count that we don't need.